In this presentation, we are talk about Carnot's theorem. According to Carnot's theorem, all reversible engines working between the same two temperature limits have the same efficiency. No heat engine can be more efficient than a Carnot's reversible engine working between the same limits of temperatures. You know the efficiency formula. Efficiency of an engine is given by the formula eta equal to Q1, the amount of heat energy taken from the source, minus Q2, the amount of heat energy rejected to the zinc, divided by Q1. Here Q1 minus Q2 is our W, work done. The amount of energy converted into mechanical work is important in thermodynamics. Suppose the heat energy may not be converted into mechanical work, such heat energy is called as unavailable energy. This is equal to 1 minus Q2 by Q1, which is equal to 1 minus T2 by T1. T2 is the temperature of the zinc, T1 is the temperature of the source. Here T1 is greater than T2. See the efficiency formula. Eta is depending upon the values of T1 and T2. Eta is independent of the nature of the working substance. So different engines specify different working substances. If you allow all the engines to work between the same two temperature limits T1 and T2, they may have the same efficiency. This is called Carnot's theorem. To prove this, consider two reversible heat engines A and B working between the temperature limits T1 and T2. T1 is the temperature of the source, T2 is the temperature of the zinc. T1 is greater than T2. Allow the engine A to be coupled with B using a suitable machine. Assume engine A is more efficient than engine B. Assume eta A is greater than eta B. Now, A serves as a heat engine while B serves as a refrigerator. Here the engine A is called heat engine since it absorbs heat energy from the source and rejects heat energy to the zinc. In the case of engine B, it is acted as a refrigerator. It absorbs heat energy from the zinc and rejects heat energy to the source. It is working in the reverse order. It takes heat energy from the cold body and gives heat energy to the hot body. So it is a refrigerator. We have tied the two engines with the help of a suitable machine. Therefore, we may get a complete cycle. Engine A is working in the forward direction, engine B is working in the reverse direction. During each cycle, A absorbs a quantity of heat Q1 from the source at T1, performs work W, and rejects a quantity of heat Q2 to the zinc at temperature T2. As we pointed out earlier, the thermodynamics talks about the amount of heat energy converted into mechanical work. The engine A absorbs Q1 amount of heat energy from the source and converts some amount of energy into mechanical work, and the remaining amount of energy which cannot be converted into mechanical work is given to the zinc. Therefore, work done is equal to Q1 minus Q2. When B cycles in opposite direction, which means that B works in the opposite direction. It absorbs a quantity of heat Q2 dash from the zinc, which is at the temperature T2. The engine B is working in the opposite direction to that of A. Therefore, B absorbs Q2 dash amount of heat energy from the zinc. We know that zinc is at the lower temperature. The engine B takes out heat energy from a body at a lower temperature and gives heat energy to a body at a high temperature. Here, engine B absorbs Q2 dash of heat energy from the zinc at a temperature T2. The engine A performs work on engine B. Already the engine A is having the work W. It performs work on engine B. As a result of this work done, engine B rejects Q1 dash amount of heat energy to the source. Therefore, Q1 dash is equal to Q2 dash, the amount of heat energy absorbed from the zinc by the engine B plus W. This is work done carried out by the engine A. Therefore, W equal to Q1 dash minus Q2 dash. From the equations 1 and 2, Q1 minus Q2 equal to Q1 dash minus Q2 dash. If the engines A and B are having different efficiencies, we assumed that engine A is more efficient than engine B. We can write Q1 minus Q2 by Q1 is greater than Q1 dash minus Q2 dash by Q1 dash. From this you may write Q1 dash minus Q2 dash divided by Q1 dash. Here Q1 minus Q2 by Q1. This is equal to 1 minus Q2 by Q1, which is greater than 1 minus is Q2 dash. Q2 dash divided by Q1 dash. From the above equation, the quantity Q2 by Q1 should be lesser than Q2 dash by Q1 dash. See here, the entire should be greater than this. Therefore, Q2 by Q1 subtracting factor should be lesser than Q2 dash by Q1 dash. Therefore, the value of Q1 should be lesser than Q1 dash, or 1 by Q1. 1 by Q1 should be greater than 1 by Q1 dash. From this, it is clear that the value of Q1 is lesser than the value of Q1 dash. Q1 dash should be large. The amount of heat energy given to the source should be greater than the amount of heat energy taken from the source. Similarly, we can write Q2 dash is greater than Q2. This demonstrates that the quantity of heat Q1 dash rejected into the source by the engine B is greater than the quantity of heat Q1 absorbed by engine A. Similarly, the quantity of heat Q2 dash absorbed from the zinc by B is greater than the quantity of heat Q2 which A rejects to the zinc. It should be clear. The engine A absorbs Q1 quantity of heat energy, whereas the engine from the source, whereas the engine B rejects Q1 dash amount of heat energy to the source. If A is more efficient than B, we have reached a condition at which the amount of heat energy rejected to the source is greater than the amount of heat energy taken from the source. At the same time, Q2 be the amount of heat energy rejected to the zinc by the engine A, whereas Q2 dash is the amount of heat energy taken away from the zinc by the engine B. Here, the amount of energy taken away from the zinc is greater than the amount of heat energy given to the zinc by the engine A. If you assume that engine A is more efficient than engine B. Hence, during one complete cycle, a quantity Q1 dash minus Q1, which is equal to Q2 dash minus Q2, will be transformed from the zinc to the source. This means that heat energy is transferred from a cold body to a hot body without the help of any external agency. Hence, the efficiency of A is equal to efficiency of B, because according to the law of thermodynamics, second law of thermodynamics, it is impossible to transform heat energy from a cold body to a hot body without the help of any external agency. If A is more efficient than B, we have arrived at the condition that the heat energy is transformed from a cold body to a hot body, which is highly impossible. Therefore, we may conclude that all the reversible engines are having same efficiency. Our assumption eta A is greater than eta B is wrong. Eta A equal to eta B is correct. This is our Carnot theorem. If you assume engine A is more efficient than engine B, the amount of heat energy given to the source with the help of the engine B is greater than the amount of heat energy taken away from the source by the engine A, and the amount of heat energy taken from the zinc by the engine B is also greater than the amount of heat energy rejected to the zinc by the engine A, which is practically impossible.